Classical Physics Tutoring, Chapter 3, Section 4, Light Wave. We go over a little bit about light wave. Actually, light is not the wave. The correct to say light is a quantum. Now, light is a quantum, but one time historically, scientists thought it's a wave, and they tried to prove it's a wave. But wave cannot propagate without medium. In the vacuum, light propagates. So that was a big controversy for one time. And what they did is they assume existence of ether. It's filled everywhere in the space, and the light uses ether as a medium. Now, when the Earth is rotating, they try to prove that the light's coming this point and this point. It should have a different the observation result, but they couldn't prove that this light is like a wave. It has a different speed, the observed by two different points of the Earth. Okay, so it's correct to say the light is a quantum and behave like a wave, but it behave like a quantum also. So the compromise idea is must be a kind of pocket wave. So if you use the approximation, it's just like the point mass. There is a center point, and that's treated like a quantum, but the whole thing is like a wave. So it has a duality. Okay, but this packet sometimes spread all over in the space, so it's hard to explain. The truth is, we still do not understand the underlying mechanism of the quantum wave very well. We start having some understanding on the quantum wave, but this is beyond this classical physics subject, so we don't get into that. But light should be actually introduced after electromagnetic theory, the Maxwell's electromagnetic theory, because light is actually EM wave, and we're getting plenty of EM wave from the sun light. Okay, and it's behaved like a wave, but Higgins Principle does not apply. It's very peculiar things about light. When you say light, what is light actually? It's microwave is light. The gamma ray high energy particle is light. There are so many light. So let's look at this overall. When we say light, what is included? It's electromagnetic wave, and like we use a cell phone and signal or microwave oven 2.5 gigahertz. Okay, that's a kind of light too, EM wave. And the 4G and the 5G, these are all categories. It share the same characteristic, but the interaction with molecules quite different. The heat up molecule at a certain frequency depend on, for example, the heat up water molecule at 2.5 gigahertz around there. So it depends on the size of molecules. The light wave lengths come into the play. Okay, and we have a visible light. Beyond that, ultraviolet. Ultraviolet is very high energy, and the light energy and intensity, you have to separate. Intensity is how many number of light particle you have, but energy level is related to frequency, and ultraviolet is 700 nanometer wave. very high frequency, but it can be just one single light. So we have to separate intensity and energy of the wave. Okay, and when the light energy is very high, it may break the molecule bonding, and that kind of energy is good and bad. The good is to synthesize a new molecule, like the tree create the energy starch using light energy, but the human skin may get the cancer because it's break the DNA. Okay, and that's ultraviolet. And beyond that, we still have a light. What kind of light? X-ray. This kind of light. And beyond that, the energy level is indicated by electron volt. Okay, this goes through human body, is passed through. And gamma ray is, even some of them go through building, right, or mountain. So and when it's hit any organic molecule in the human body, for sure it's break the bond and the molecules change, and sometimes bad things happen in the body. So that's why we have to avoid those high energy. So that's all in the category of light. Microwave, low energy, these are harmless, those Wi-Fi energy, and actually even oven microwave is harmless. Why it's harm? Because if you heat up water in your body, often it may have a different some bad effect, health effect, but this light doesn't break any molecule in the body. Okay, so that's kind of light. So we have a light which is an electromagnetic wave, and the electromagnetic wave is not longitudinal or transverse. Transverse, well, it's not really transverse either. It doesn't belong to any, and it has the two wave composite moving together, the magnetic field and the electric field intertwined. And this kind of wave is not really a wave so far we learned. It's a totally different wave. So actually we should put that in the electromagnetics chapters, but historically the wave was studied as the light was studied as a wave. So we talk about that extent. So what does light do? This is the speed, very fast, and it goes straight in the uniform medium, and it's independent to each other. The light waves still interfere each other, but as a independent variable. Say if light wave 1 and light wave 2, they don't interact, but interference pattern we can see. Wave 1 and wave 2's overlap. Okay, but the Higgins principle imply that two waves interact each other through medium. One wave change the medium, and it's affect it's easier to assume they're independent because you can just adapt the wave equation to see the interference. But in reality, like a medium, for example, medium is oil, it's a sticky substance, and it has the internal friction. Then you just simply adapt the two wave equation. Doesn't reflect the really interference pattern. It's start deviating from the interference pattern. And another things about limitation of Higgins principle on the light is Higgins principle assumed the wave is forward going, right? So if you whip the rope, it's affect the neighbor's rope and keep moving forward. but the light can go backward. So if you make a light blip, this one and another one go here. Okay, so the Higgins principle, you envelope the wave front and make a wave line, and that's not that easy because it's generated on the both direction. Okay, that's what it means, may propagate backward. But light shows refraction law exactly like regular wave, and refraction law too, and that's why it's confused scientists. Light must be a wave, but Higgins principle doesn't work in the vacuum. Okay, so it's something wrong here. And also diffraction characteristic, and the famous double slit diffraction characteristic, this is very unique to light, and you cannot see it in the regular wave. Only light have this kind. Okay, now light interact with molecules, so refractive index, there is the refractive index in the medium. So if you have a bunch of molecules, light slow down a little bit, so speed change a little bit, and that's why we have this. But this is kind of different from wave. Wave, we explain this Snell's law using Higgins principle, right? Okay, but the light, the mechanism is different, but still we have a Snell's law for the light. Okay, that's the refractive characteristic. Now the scientists actually formulated a new way to think about the light. Why has a reflection and refraction? Okay, suppose you have a source A reach to B, right? And there are many ways to reach B, and if you think about the total lengths to reach B, okay, we integrate along the path, which path is the shortest. So it's going to be minimum path principle, right? Okay, so this minimum path is if you have the source of light and it's hit the screen, and say you have a slit, okay, go through here, go through here, go through here. Okay, so the light is considered that it knows the minimum path. Wait a minute, light doesn't have a brain. Light look at situation and decide which path to go. This is very peculiar, strange things about it. Light seems to know always which way is the minimum way to reach here. Okay, and occasionally it's take the wrong path, but most of the time minimum path. Okay, so that's what this equation is about. You take the path lengths and integrate by the path, get the total length. This is called principle of minimum path. So this is a replacement of Higgins principle. The light wave seems like it knows the minimum path, and that seems to match up with the experiment very well. Now refraction, we know the lens, we use a refraction, say this is orthogonal to the surface, then lights come in theta 1 and theta 2, and it's hit here. So this is a focus point. Okay, and using this equation, we can determine what is the curve requirement to get the single focus point, and that's going to be convex lens and concave lens. Okay, concave lens is like incoming is theta 1 and go out theta 2. This is orthogonal to the surface. Okay, and having a virtual image at the focus point. In order to have a single focus point, what kind of curvature is required? Okay, and this is gonna be turned out to be a parabola curve, not a sphere. The sphere lens cannot have a single focus point. It's going to, every incoming is going to have a different focus point, and that means the image is going to be blurred. Okay, so this is the lens. We don't have a time to go details, but there are a lot of literature about how to calculate the focus point and the curvature of the lens, and how to combine the lens to get the effective magnification. That's a microscope and telescope design. Okay, so that's a kind of science. It's well advanced before we found out that light is quantum. So we already know the lens is not sphere shape. It's a parabola shape. Okay, and interference of light. Suppose we have two waves interfere each other. Okay, so this is equation here, because each light is a frequency, same frequency f, and phase is different, phase theta 1, theta 2, and it's going to the same direction. So when they overlap, what kind of wave we get? Okay, so that's the interference. But interference in a sense that the light pattern is overlapped. It doesn't really change the wave each other. They don't interfere in that sense. You just have interference patterns. So the light wave, since they are not depending on the medium, there's no way to interfere each other. They are independent light. Only things you see is interference pattern only. Okay, so another important things about light is there is a polarization. The direction, its electric field is y and magnetic field is z, and it can be filtered out by y direction or z direction, and still light propagate with just a single polarity. Okay, so the light is polarized. That means it has a two different transverse wave, and interference condition is very complicated once you start thinking about polarity. Okay, light from the same source has a parallel polarity, and they do interfere at each other. So in the same source, this light and this light use mirror to direct, to let them interfere. They interfere because the same source and has the same polarity. When the light from the same source has a vertical polarity, it will have the interference only when one is changed to the parallel and at 180 degree. So when you have two different source 1, source 2, and has a vertical polarity relationship, somehow we have to correct this to parallel. That means we have to rotate this transverse wave and adjust the phase 180 degree, then it's interfere. Two vertical lights do not cause interference. If source 1, source 2, they are vertical polarity, then they don't interfere at all. Okay, and one of two vertical lights change to the parallel to the others, it will not cause interference. Okay, until you correct the phase, it will not interfere. So it's very complicated condition for interference. It's not simple that, you know, wave 1 and wave 2 just add up. No, it's the polarity coming to play. So that's a light. Okay, so we're going to go through more on the light wave in the electromagnetic sections, but this is kind of things the scientists observed even before they find out light is not just wave. It just shows a wave characteristic, but actually it's a quantum. And do you know how quantum works? Honestly, we just start understanding some of it. The underlying mechanism of quantum is still unknown. Okay, and that's a very fascinating field, new field of physics. And after you have enough knowledge in the classical physics, you can move on to the quantum mechanics. Okay, so that's the tutoring for today, and I hope you enjoyed, and if you like, subscribe.